Hello friends, in this video we are going to see working principle of a DC motor. The working principle of a DC motor can be told in just a single statement, and that is when a current carrying conductor is placed in a magnetic field, it experiences a mechanical force. So basically, in a practical DC motor, the flux is created by field winding. And armature conductors play a role of current carrying conductor. So we are going to excite armature winding so that it will carry current, and those conductors we are placing in a magnetic field caused by field winding. Hence, there will be a mechanical force on each conductor of armature winding. These armature conductors are placed in a slot in the periphery of armature. Every conductor experiences a mechanical force, and that will produce a twisting action which will generate a torque. Hence, armature starts rotating. Let's see this phenomena diagrammatically. So here we are having a magnetic field produced because of these poles. Obviously, flux lines will be from north pole to south pole. In this magnetic field, you are going to place a conductor which will carry a current towards paper. So that is shown by a cross. As per the right hand thumb rule, there will be a magnetic field associated with this conductor which will revolve around it, and that is given by this thumb rule. It states that if this is a current carrying conductor, then magnetic field will be represented by curved finger if thumb is in the direction of a current. So if I apply that, you will get a magnetic lines for this conductor in a clockwise direction. So if you see here, in left half I am getting addition of two fluxes. One is caused by the field winding and another is caused by armature winding. So here I can say addition of fluxes are happening. And on right hand it is cancellation of two fluxes. So effectively this diagram will look like this. I have addition of flux line over here, whereas here weakening of flux happening. So here gathering of flux, whereas at this side it will be weakening of fluxes. Now there will be a force exerted from high flux density to low flux density. actually this flux lines will act like a stretched rubber band under tension. So that will experience a force in this direction. So ultimately every conductor experiencing this sort of force, since I told earlier all the conductors are placed in the slots of a periphery of armature, so all these forces ultimately contributed a twisting action or a twisting motion which we called as a torque, and because of this torque armature starts rotating. So this is a simple principle of working of a DC motor. Now let's see the direction of rotation of a motor. The magnitude of the force experienced by the armature conductor is given by F equal to B L I Newton, where B is magnetic flux density, produced by field winding. L is the active length of a conductor. And I is the magnitude of a current carrying by a conductor. This force is a vector quantity, so it will have some direction, and that direction is determined by Fleming's left hand rule. So let's see what this rule is all about. So Fleming's left hand rule states that outstretch the three fingers of the left hand, namely first finger, middle finger and thumb. So it is like this. So consider a left hand, three fingers, first finger, middle finger and thumb outstretched such a way that they are mutually perpendicular to each other. Now point the first finger in the direction of magnetic field. That means this finger is in the direction of magnetic field. Middle finger in the direction of current. This is the direction of current. Then the thumb gives the direction of the force experienced by the conductor. So Fleming's left hand rule will tell you what will be the direction of force experienced by the armature conductor. Let's illustrate this with various cases. Now case number 1, I am having the poles like this. This is the south pole, this is north pole. So obviously flux will be from north to south. In this field, I am placing a conductor carrying a current towards the paper. So I have shown by cross. So let's apply Fleming's left hand rule to this. What it states? first finger should be in the direction of field. Middle finger should be in the direction of current. So current going in the paper, therefore this direction. So outstretched thumb will tell you the direction of force. So if I apply Fleming's left hand rule, I will get direction of force this way. So this is a case number 1. Let's go to the next case. I am placing poles such a way that the magnetic field is of the same direction. It's north to south. And this time armature conductor carrying current which will take out of the paper. So it will be represented by a dot. So it is coming out of the paper. Let's apply Fleming's left hand rule. So once again magnetic flux. This time current carrying conductor is like this. So outstretched thumb will have this direction of force like this. So this will be the direction of force. So what I have done, if I compare first and second case, I will come to know that direction of force has been reversed just by changing the direction of current in the armature conductor. Let's go to the next step now. This time I will change the pole's location. So this will be north, this will be south. Flux will be from north to south. Placing a armature conductor which will carry current shown by cross means in the paper. So if I apply Fleming's left hand rule for this, north to south in the paper, so it is a bit difficult for me to show, but if you do it, you will come to know that the direction of force will be this way. Case number 3. In case number 4, poles locations are like this: north, south. So flux will be from north to south. Armature, a place which will carry current shown by dot towards user. So if I apply Fleming's left hand rule to this is a flux current carrying conductor, and this will be the direction of mechanical force. Case number 4. So what we have seen over here, suppose I want to change the direction of force experienced by an armature conductor. Either I should change the direction of current of armature conductor, or I can change the direction of current for field winding so that it will change the orientation of north and south pole. So what does that mean? To reverse the direction of rotation, either direction of main field produced by the field winding is reverse, means case 1 and 3. What I have done in 1, flux lines are upward, here downward. But armature carrying a current in same direction, but still force are in reverse direction. Or direction of the current passing through armature is reverse. Case 1 and 2 means in 1 I have a conductor carrying current shown by cross towards paper. In case 2, conductor carrying a current away from the paper or towards the user or observer. So I have changed the direction of a current, but magnetic flux having the same direction, north to south, north to south. Force experienced are in the reverse direction. So because of this, we can say in order to reverse the motion direction, either I can change field winding current or armature winding current. Let's see next concept, and that is back EMF. Once motor starts rotating, its conductor will cut the magnetic flux produced by field winding. So, by Faraday's law of electromagnetic induction, there will be a EMF induced, just like EMF induced in case of DC generator. So, though it is a motor, but when conductor starts rotating because of motoring action, it will cut the magnetic flux and produce the EMF, which we call as back EMF. So obviously back EMF is generated by the generating action. What does that mean? Moving conductors cutting the magnetic flux. So obviously the back EMF will have the equation that is same as the EMF equation of a generator, and that is given by phi p n z upon 68. We will consider this as EMF equation of a motor. Where phi is the flux per pole, p number of poles, n is the speed of rotation of a conductors given in RPM, z total number of conductors, and a number of parallel paths in which total number of conductors are divided. The EMF equation is produced because of Faraday's law of electromagnetic induction. And its direction is given by Lenz's law. What it say? EMF will oppose the flux which produce this EMF. So basically, effect opposes the cause. So direction will be opposite to the supply voltage. This is as per Lenz's law. Now I want to draw a equivalent circuit of a motor. So how it will be? This is a back EMF produced. Armature resistance is Ra and supply voltage will be like this. So if you see over here, the back EMF is generated such a way that it will try to oppose this armature current which is produced by this supply voltage Vs. So equivalent circuit diagram will be I am taking this armature resistance along with this back EMF. This is excited by a supply voltage Vs. It produce armature current Ia. So voltage equation for this is Vs equal to IaRa plus Eb plus some voltage drop across brushes. So here IRA is armature drop, or you can say armature resistance drop. Eb is the back EMF and V brush is brush resistance drop. So supply voltage of a DC motor has to take care of all these three things. Thank you.